All right, hello everyone. So this should be Math 6, Day 6. Again, you'll be watching this before we meet in class. So we just, on our previous day, went over a lot of different terms. Hopefully some of them review. If not, hopefully we got questions answered in class. And then today we're going to be going over lessons 26 through 30. Similar to we did the previous day, just hitting some of the highlights, doing a few quick examples, making sure the vocabulary makes sense, and then going over more in depth in class. So today, lesson 26, using manipulatives to reduce fractions, adding and subtracting mixed numbers. Again, a mixed number is just a number with a fraction. So the same rules of common denominators for adding and subtracting fractions, that will apply to mixed numbers as well. Now, manipulatives, they are very helpful if you're kind of a visual learner or you're still kind of struggling with what exactly a fraction is. A lot of times they'll be drawn in these forms of circles and how many parts, or we could draw rectangular boxes in order to divide it into different parts. So you'll see it in different ways. Again, if you're more visual than me, this may really help you. I personally just like doing the math right up front. But again, this may help you as you go through and just kind of to visualize what a fraction is, or as we get into percentage, what a percent is. Okay, so this is our whole. So whether we divide it into 8 pieces, 6 pieces, 4 pieces, or 2 pieces, okay, it's still a whole. So if we look at 4 of our 8, okay, well, it's still half of the circle is shaded. So 4 of the 8, that would reduce down to 1/2. 3 of our 6 pieces are shaded. Well, 3, 6 reduces down to 1/2. 2 of the 4, but half of the circle is shaded. 2/4 reduces down to 1/2. So this is just kind of showing when we reduce fractions, that's why we do it. The first few tests I'll probably be nice and I won't take points off if you forget to reduce fractions, but down the road as we get very familiar and do this more and more, the expectation is that you always reduce fractions, unless for whatever reason you're told to leave it in whatever form, which very rarely can I think of any examples where it asks you to do that. And so that's what we mean when we reduce fractions. So again, you can use a manipulative to reduce 2/6. Okay, again, we look back up at the one where we have this divided into 6 equal sectors. 2 of the 6, okay, well, how much of your circle is shaded? And we look at that, okay, 2/6 plus 2/6, that would be 1/3 of our circle. And what I think is easier is just reducing using the numbers. So what we do when we reduce, we look for common factors, or what's the largest number. We don't have to start with the largest number, but it will make things faster. If we don't know the largest factor right away, we just start simplifying until we get to where we can't simplify anymore. 2 and 6 are not very large numbers, so pretty easy to figure out that 2 goes into 2 and 6. So we say 2 goes into 2 one time, 2 goes into 6 3 times. Okay, so we factor a 2 out of 2. We're left with 1. We factor a 2 out of 6, or really 6 divided by 2. We're left with 3. And then we can't reduce that down anymore, so that would be our most simplified form. Okay, so that's how I would do it again if you're visual. And if it asks you on the homework and you prefer just to do it the way that I did, I'm fine with you using either method. I think this kind of helps you to introduce fractions and get comfortable and familiar with them. But if you already feel pretty good with them and you don't need to do that, and you want to just go right into reducing the fraction or using the fractions, then by all means, go ahead. Adding and subtracting. So if we have 1/3 and 1/3, so 2/3 of a circle is what percent of a circle? Well, we have 1/3 plus 1/3. And we'll show you how we can convert fractions to percentages down the road. They've already done it for us. We would either get this all over 100, or we would do 1 divided by 3 and get a decimal number and then multiply it by 100 to get our fraction, or sorry, percentage from our fraction. But 33 and a third percent, so 33 and a third percent is the same as 1/3 as a fraction. So 33 and a third plus 33 and a third, we would add those together. So 33 plus 33 is 66. 1/3 plus 1/3, we just did that. Oh no, we didn't do that up here. We just simplified. 1/3 plus 1/3 would be 2/3. So 66 and 2/3 percent. So again, just like when we have decimals or we have 2, 3-digit numbers, we just add up our places, our ones, our tens, our hundreds. Same thing here. We add up our fractions, and then our ones and our tens. So 1/3 plus 1/3 is 2/3. 3 plus 3 is 6, and 3 plus 3 is 6. It's the same thing we do whether it's decimals, single-digit numbers, 2-digit numbers, 3-digit numbers. We just line them up, make sure the fractions, the ones place and the tens place all line up, and then add them together. 2/6 of a circle is what percent of the circle? And they gave us the percent, 16 and 2/3 percent. So 2/3 and 2/3 is 4/3. So we'll show you how to do that. So 16 2/3 plus 16 2/3. Well, 2/3 plus 2/3 is 2 plus 2 is 4. Still thirds, still over 3. And we'll show you how. Okay, this is an improper fraction, so we'll need to do something with that at the end. 6 plus 6 is 12. Carry the 1. 1, 2, 3. 1 plus 1 plus 1 is 3. So 32 and 4/3, but this is a mixed number with an improper fraction, so we need to convert this to a mixed number. 4/3. 3 goes into 4 once with 1 left over, so 1 and 1/3. So 32 plus 1 and 1/3 becomes 33 and 1/3. Okay, or 1/6 of a circle. 1/6 plus 1/6 is 2/6, which reduces down to 1/3. In the previous example, we just saw that 1/3 is 33 and a third percent. 33 and 1/3. Okay. When we're subtracting, okay, same thing. We just do the same order we would if it was a decimal or just a whole number. 3/8 minus 1/8. Those are a fraction. That gives us 3 minus 1 is 2/8. 5 minus 1 is 4. And then 2/8, since 2 goes into both of those, we would factor out a 2, which would leave us with 1/4. There's your practice set. We'll go over that when we return to class. 27. Okay, measures of a circle. So just some different terms. Diameter, that's from one side of the circle to the other going through the center. If it doesn't go through the center, that's going to affect the measurement. It wouldn't be a diameter. And this is true from any point to any other point on the circle as long as you go through the center. It's the same distance. Just because it's drawn horizontally, it doesn't have to be right there. A radius is exactly half of the diameter, and then the circumference with circles, for whatever reason, we don't call it perimeter, we call it circumference. So that's the distance around the circle is circumference. And then if we have plural, if we're talking about multiple of the radius, we call it radii. I know it sounds kind of weird, but we don't say radiuses. If you do, I'll know what you're talking about. But the technical term, multiple radii. Example 1, what is the perimeter of a circle? Okay, again, if you accidentally say perimeter, we'll know what you're talking about. Just perimeters are usually what we reference when we're talking about polygons that have straight edges. Circumference is what we reference when we're talking about a circle. Example 2, if the radius is 4 centimeters, the diameter would just be double that or times 2. So 4 times 2 would be 8. So if you know the radius, the diameter is pretty easy to solve, and vice versa. If we knew the diameter, we could work backwards to find the radius pretty simply. And again, we'll do a lot more. This is just brief introduction into circles, but we'll do a lot more with finding the area, circumference, different things within a circle. All right, angles. We all know what angles are. Okay, so in mathematics, a plane is a flat surface that continues on infinitely in all directions, and it's two-dimensional. Okay, if we have a line, it's one-dimensional, but it continues on infinitely within a plane. If we have parallel lines, that means that they're going to run forever and they're never going to cross. They're never going to intersect. So they're parallel. They would never be pointed up or down at each other. That would cause them to cross. Perpendicular means they meet at right angles. So it makes this cross shape, and then every angle of intersection is a 90-degree angle. If lines intersect at a point but are not perpendicular, the lines are oblique. Okay, so parallel, perpendicular, oblique. Where lines intersect, angles are formed. So here's just some different angles that we have. Okay, it can be in any orientation here. Okay, we have different names for angles, as we'll find out in a second. This is called our vertex of our angle. It could be two endpoints. We could have two line segments. We could have rays or lines that create these angles. Okay. Vertex right there. Again, we'll probably abbreviate. We could write angle B, but usually we use this symbol. Let me highlight right there to indicate angle B. I know it looks similar to the greater than or less than symbol, but it's just angle B. So we just use that to save time versus writing out the word angle every single time. Another way we can refer to it is if we have 3 points, we can refer to it as an ABC or CBA. And we go 1, 2, 3, or 3, 2, 1. We can't call it ACB angle because that's not it. B is in the middle, which means it is our vertex. Okay, so if we said in this example, if we said angle B or angle ABC or CBA, we would be referring to the same angle down here. Right angles, I've probably used that without even realizing that we maybe haven't talked about it a ton, but a right angle is a 90-degree angle, and it'll be marked with a small square right there. So that's not an internal shape or anything within that. That's just indicating that this angle is 90 degrees. Acute angles are then less than 90 degrees. So as we see right here, these ones are smaller than 90 degrees. We can get out and measure them or calculate them, but we can just look at them and tell that they're obviously acute. And then the angles that are larger than 90 degrees are obtuse. So an angle can be a right angle, or it can be less than 90 degrees and be an acute angle, or it can be larger than 90 degrees and be an obtuse angle. So if we're looking at example 1 right here, name the acute angle. Well, it looks like, and we can't just call it, in this case, M, because we don't know if M is referring to this right here or this right here. So it looks like this angle right here is less than 90 degrees. It's our acute angle. So I would say RMQ, angle RMQ or QMR, either way. That's our acute angle. And then the obtuse angle, and we can't just say angle M because we don't know if that's this small angle, this obtuse angle, or this entire angle, which is 180 degrees, could be referring to 3 different angles. So we have to be more specific. The obtuse angle would be RMS or SMR. Okay, then if we were given example 2, we were given a shape. This looks like a trapezoid because we have 2 right angles. So we have 2 sides that are going to be parallel and opposite sides that are not. So if in this figure, angle D, and it's an enclosed quadrilateral, so we can just refer to the 4 different angles. We can still call it A, D, C, or C, D, A if we want to, but since it's enclosed, we can just say angle D, angle C, angle B, and angle A. Angle D is right. It looks like C is also a right angle based on this mark. So we know angle C is a right angle for A. Which is acute? Well, it looks like A is obviously less than 90 degrees because 90 degrees would be going straight down to the base, and it's going at an angle which is making this smaller. And then that's causing angle B to be larger, which is the obtuse angle. Okay. So right acute obtuse. Okay. Multiplying fractions and reducing fractions. So again, we talked about fractions. If we're looking at multiplying 1/2 by 1/2, again, we can use our manipulatives or circles or rectangles, whatever we want to do to show it. Again, I think it's easier, and especially as we get into more complex fractions, to just do the multiplication. But if I have 1/2 of, again, of means multiplication. In multiplication, we use this symbol or the X symbol or eventually parentheses. 1/2 of 1/2. In this case, when we multiply fractions, we don't have to have common denominators, which actually makes it a little bit easier in my opinion. We don't have to manipulate or rename. We will possibly have to reduce at the end, but that's the same with adding or subtracting. So in this case, we multiply our numerators. 1 times 1. Yeah, that's pretty easy. That's 1. And we don't just bring over the 2. We have to multiply our denominators. 2 times 2 is 4. So a fraction times a fraction, we have 1/2 of 1/2. That gives us 1/4. So it causes it to go down. Okay, so it actually got smaller. Usually we think we're multiplying something, we're making it larger. Usually that's the case, but if it's a number less than 1, okay, 1/2 of 1/2, and if you are given $50 and you have to split it with your brother or sister, now you have 1/2 of $50. You have a quarter, okay, or 1/4 of a dollar. Okay, so that's multiplying our fractions. Okay, 1/2 of 1/2, 1/2 times 1/2 is 1/4. 1/2 of 3/4, again, if visually you're good at drawing and this really helps you, by all means, please do it. For me, it actually starts to make it almost look more confusing. So I don't like to use that. I just like to multiply. But again, you can look through and just see, well, I have, 1/2 of 3/4. So draw 3/4 of a circle and cut it in half, figure out your fraction. Again, I think it's a little bit easier just to do the multiplication. 1/2 of 3/4. Okay, 1 times 3, 2 times 4, okay, 3/8. I think for me, drawing, a circle, getting it out, and then trying to draw even sectors and make it visually appealing so it actually looks accurate, and then go through and shade in the portion and then cut it in half. Again, you can do that. To me, it just seems like more work. If that helps you, by all means, please do so. We have 1/2 of 3/4. Multiply numerators, multiply your denominators, and then 3 and 8, we don't have any common factors, so there's nothing we can do to reduce, so we would be done. Okay, reducing fractions. So all of these, for even whole numbers, if we have 4, we can rewrite it as 4/1. So again, just because it's a whole number, it doesn't have a denominator, we can always write it as being over 1. 1/1 is 1. 2/1 is 2. 3/1 is 3. 4/1 is 4. So that's a good reminder if you don't remember that as you're multiplying against. That way you have 2 numerators and 2 denominators. It's probably going to make it a little bit easier. When it's written like this, you're like, well, it's in the middle. Do I multiply it by the 2 or the 3? But then if you write it as a fraction, it looks more clear of what we need to multiply and what we need to divide. And then it would end up being, in this case, an improper fraction, which, unless the test or review or homework or whatever says write it as a specific mixed number or improper fraction, I will usually accept either way. As long as it's reduced, you leave it as an improper fraction or a mixed number. Unless it told you to do one or the other, you can leave it as either, and I will accept that. Because 8/3 and 2 2/3 are equivalent to each other, and they're both reduced. Now, reducing fractions, this will be something that becomes really second nature as we do it. We're going to factor out numbers. And if we can find the greatest common factor, as we talked about in a previous lesson, that acronym GCF, greatest common factor, it'll just save us a lot of time. So let's look at the example 6/12. And let's say let's say we forgot our multiples, we forgot greatest common factor, we can't see it right away. Well, let's just start with what we know, okay, the rules we talked about. Well, both of these are even numbers, so I know 2 goes into it. So 2 goes into 6 3 times. It goes into 12 6 times. Okay, so I've reduced it down. Oh, but then I say 3 goes into both of these numbers. So 3 goes into 3 once. It goes into 6 2 times. So I could, especially with larger numbers, as you may not just instantly see what the greatest common factor is. You may have to reduce until you can't anymore. We can also use prime factorization, which we'll show you down the road of how to do that and reduce our prime numbers if we have common ones in the numerator and denominator. But just keep reducing until you can't anymore. But if we do know the greatest common factor, that's going to make life a little bit easier. We're going to save steps. Okay, 6 and 12. Oh, I know 6. We did 2 and then 3. 2 times 3 is 6. So we still did it correctly and got the right answer. But if we know, oh, 6 goes into 6 and 12. Oh, 6 goes into 6 once, and it goes into 12 twice, 1/2. Obviously, we arrived at the same answer, but this saved us a lot of time since we were able to see right away what the greatest common factor is. So just keep reducing until you can't anymore. But if you can figure out what that greatest common factor is right away, that's going to save you a lot of time. So let's look at 8/12. 8/12. Okay, I want greatest common factor. I know they're both even. 2 goes into them. 3 doesn't go into them. It does go into this one, but not this one. 1 plus 2 is 3. So it goes into 12. Doesn't go into 8. 4 times 2, 4 times 3. Okay. 6 goes into this, but not 8. 8 goes into this, but not this. So it's looking like 4 is our greatest common factor. So again, we're factoring out of 4. We're dividing by 4. So 8 divided by 4 is 2. So when I factor a 4 out, I'm left with 2. 12 divided by 4 is 3. I factor out a 4. I'm left with 3. So 2/3. And I cannot reduce that anymore. So I would be done. Okay, let's say we did what we forgot. And we just say, oh, 2 goes into both of them. 2 goes into this. Oh, but then 2 also goes into these. Okay, same answer, is just one step, and this one took 2 steps to get there. Still got the same answer, still got it correct. If we know common factors, we have to find those. But if we can find the greatest common factor, it's going to make it even easier. Okay, and then last one, least common multiple, or just like greatest common factor, we'll often see it like this acronym, LCM. Then looking at reciprocals. So multiples we talked about just previously, 2, 4, 6, 8, 10, continuing on infinitely, 3, 6, 9, 12, 15, 18. So greatest common factor, when we're reducing or taking a number out, we want to find the largest number that we can do between both of them. When we're multiplying out, we want to find the least common multiple. Because again, 2 and 3, we could go all the way out to 300, 600, 1200. 2 and 3 goes into 12 million. 2 and 3 goes into both of those. So there's going to be infinite numbers that they both go into. So we don't want to find the greatest common multiple, because really that we literally go on forever. We want to find the least common multiple. So in this case, we're going to go 2, 4, 6, 8, 10, 3, 6, 9, 12. So we already found some common ones, but the least would be 6. 6 there and a 6 there. So that's the least common multiple. So if we're looking at 3 and 4, again, you can write these out like we do horizontally, or you can kind of get in the rhythm where you do them mentally and figure it out. So 3, 6, 9, 12, 15, 4, 8, 12, 16. 12. So the first number that shows up that they have in common, that is the least common multiple. And let's say we had an example like 4 and 8. 4, 8, 12, 16, and so on. And then 8, we have 8, 16. Oh, well, right away we have 8 and 8. Okay, so even though 8 is the number we're looking at, it's still 8 is a multiple of 8. 8 is a multiple of 4. So this would be the least common multiple. So that could be the case too, where we only have to find a multiple of one or the other because the other one is a multiple of itself. So that's a possibility we may see as well. Okay, like we said, 2 and 4. Well, 4 is a multiple of 4 and of 2. So that would be the least common multiple. Now, reciprocals. So a reciprocal is where we just take a fraction and we just flip it. And the easiest way to explain it. So if we have 2/3, the reciprocal of that is 3/2. 2 over 3, we flip it and it becomes 3 over 2. Or if we have 2, the reciprocal of that, because 2 we can write as reciprocal of 2. Well, 2 we can also write as 2 over 1. Okay, and then the reciprocal of that, we just flip. So 1 goes up top, 2 goes into the denominator. So the reciprocal of 2 is 1/2. And then any number times its reciprocal is 1. Because again, 2 we can write as 2 over 1. This would give us 2 over 2, which reduces down to just 1. So it's not just true of 2 and 1/2. That's any reciprocal. So that's the example we had. 2/3 reciprocal is 3/2. 3 is in the bottom, so it goes up top. 2 is up top, so it goes in the bottom. This would give us 6 over 6. What we said, any number over itself is just 1. So any number times its reciprocal equals 1. So if you remember that rule versus doing the multiplication and then reducing it down, if you just remember, oh, it's a reciprocal, the math is basically done for you right there. So 3/4 becomes 4/3. Again, it can be an improper fraction. That's fine. Actually, one of them would have to be, okay, unless they're equal, top and bottom, in which case it's just 1. 3/4 times 4/3 is 12 over 12, which is equal to 1. So it's always going to equal 1 after we reduce. Now, you will see a lot of these problems, and I don't love the way that they're worded, but this example right here, how many 2/3 are in 1? We'll see a lot of problems like this. Some down the road, it will say how many 2/3 are in 2 or 3 or 4 or whatever. Just think reciprocal for these. Again, the way it's worded sounds really confusing. How many 2/3 are in 1? Well, you could sit there and draw out 2/3 and try and add them together till you equal 1. That would be very difficult. But if we remember a reciprocal, well, how many 2/3 are in 1, or 2/3 times what number equals 1 is an easier way to think about it. Well, how many 2/3 are in 1? Or again, 2/3 times what number equals 1? I think that's a much easier way to explain it. I don't know why they use the other terminology, maybe just to get you thinking about that 2/3 goes into 1 how many times. But again, I would just set it up. It's a word problem. I put it in standard form. Well, 2/3 times what number? Well, 2/3 times its reciprocal equals 1. So how many 2/3 are in 1? Well, that would be 3/2, or 3 over 2. So again, sounds kind of weird. There's 3/2 of 2/3 in 1. Very, very kind of muddy and confusing the way they word it. But if we remember the reciprocal and kind of phrase in the way I told you, 2/3 times what number equals 1? Well, 2/3 times its reciprocal, which is 3/2, equals 1. So I think that's a little easier way to kind of visualize it. But you will see probably these first few tests, and even down the road, even into 7th and 8th grade, you guys will see a lot of these problems. Eventually, you'll ask us for how many 2/3 are in 4. Well, what do you say? The reciprocal times 4. That's how many 2/3 are in 4. But for the most ones you'll see, it'll just be in 1. So it'll be worded like this, and you may get confused. What is that even asking? Just think reciprocal, reciprocal, reciprocal. All right, and we'll do the practice set, maybe some more examples when we get to class. Again, thank you for hanging out. I know that was a little bit to go through, but we're kind of hitting these lessons to go over some, hopefully review vocabulary and introducing possibly some new items. But I think you guys are really solid and have a lot of this down. It just, is in there. It may take a few times that we go over it, and we'll be seeing a lot of it, not just now, but down the road. So if it's not, you're not feeling 100% confident, that's okay. We have plenty of practice and plenty of time to go over these concepts. So watch these and come to class prepared, and we'll see you guys. Thanks.